Hello everyone. In today's session, we are going to explore one of the most important concepts in artificial intelligence. It's otherwise a foundational concept. How we formally define a problem so that a computer can actually attempt to solve it. So, by end of this session, you will understand what a state space is, how to represent real world problems within it, and how this framework applies to classic AI examples like chess and water jug problems. So, these are two examples that we are going to discuss in this session. Now, the first question we need to answer is first, what is your problem? So, because we're going to talk about problem definition. So, before that, we should understand what is your problem. So, when we say we want to build a system to solve a problem, so we need to go through the full complete the process. So, we cannot give a vague description. Okay, the first step is to define the problem very clearly. Okay, so that is the first step. As you can see here, the first step is to define the problem. So once you have defined the problem, next what we can do is we have to tell what exactly is the situation we are dealing with, what we want to achieve. So all these things you have to tell. So once you have told all these things, the second step is to analyze the problem. Okay, so in analyzing the problem, we have to tell what are the constraints, then what information is available to you. After defining, we have to analyze. That is the second step. The third step is to isolate the task. So what do you mean by isolating the task? You have to narrow down and tell what the agent actually needs to do at each step. That is isolation. Finally, we have to choose the best technique. Okay. So whether it's a search algorithm, whether it is a planning approach, a logic based system. So you have to tell what is the best technique you have to choose. So this four-step approach ensures that we build a system with fullest understanding of the problem. So that is very, very important. Next, we will talk about problem formulation. So the bridge between a real world problem or real world situation and then how to deal with, okay, how to deal with the real world problem. So that's what we are going to talk about here. Okay, so in this, first we should tell for a problem to be well defined. First point is we need to understand or able to describe it precisely. So that's very, very important. Okay. Next, we have to tell a problem in the AI sense. So what it actually a problem with respect to AI. So it is really the collection of, okay, it's a collection of information that an agent will use to decide what action to take. Okay, suppose think about this way. If you tell a robot to get a coffee, so what are the steps you will do? So you can just simply say, cannot say that get me a coffee. You have to tell each and every step. So you need to tell where the coffee machine is, what button to press, and coffee in hand means how it looks like. So all these things, if you describe it properly, this complete description is the problem formulation. Okay. So a well formulated problem also implies a well defined solution. Okay. So a clear path or sequence of actions that takes us from where we start to where we want to be will give you the exact or the well defined problem. Okay. Next, we will talk about the elements of a problem. So we will break down the core elements. Okay. Okay. So these elements are the building blocks for a problem. First is the initial state. Next, you have to tell about the set of possible actions. Then what is the path cost function? Then what are the or what output is actually to be achieved? We will go through it one by one. The first is the initial state. That is the situation the agent finds itself in a very beginning. That is the first state where it should be actually. For example, in a game of chess, so it's a standard starting board layout, like you have the full board layout. Okay, that is the starting position where every coin in the chessboard is placed wherever it should be exactly. That's the exact board. So, for example, if you take the water jug problem, we'll talk about that. So, it begins with both the jugs to be empty, and then you have to satisfy the constraints and satisfy the solution or bring out the solution. That is the initial state, or the agent should know where exactly it should be. Okay. Second, you should tell about the set of possible actions available to the agent. Okay. So you have to talk something about the operator. So what are the actions available to the agents so that it can reach to the state, a particular state. Okay. So tell what the agent can do. Okay. So we can call this as operators. So what is an operator? An operator is simply a description of how an action transform from one state to another state. That is called as an operator. Okay. For example, if you take a chessboard, the legal moves are the operators. Each move transforms the board from one configuration to another board, because initially we had an empty state. So once we start moving the coins, okay, so the chessboard transforms, the state space gets transformed. So we have talked about what is state space. What is a state space? State space is a set of all states reachable from the initial state by making sequence of actions. Okay, so it is one of the most important concept. Okay, so it is the complete set of all states. That is what we are trying to understand. So we'll start from initial state. So we will apply sequence of actions and then we will go to a particular state. So possible all actions. Okay. The agent's job is to navigate this sequence of actions so that it reaches the goal. Okay. Next, what is a path? A path in the state space is simply any sequence of action leading from one state to another. Okay, so the moves that you make makes your path so that you reach the final state. That is the goal state. What is the goal state? It is a function. Okay, or we say a goal test. So the goal test is a function the agent uses to check whether a given state is the goal, whether we have reached the goal state or not. Okay, so it answers the question, have I reached my destination or not? Okay, this is the goal test function. In a chess, what will be the goal? The goal test checks whether there is a checkmate or not. In a water jug problem, for example, it will check whether the 4-gallon jug exactly contain 2 gallons of water. So depending on the problem that we take, the goal test performs its function. Next, we'll talk about what is a path cost function. So the path cost functions assigns a number of the numerical cost to any path through the state. So the state space it is traveling, it will assign the numerical value. Okay, so that we can have a path cost from initial state to goal state. or through which we travel to attain the goal state. So this allows us to compare different solutions and we can find out which is the best path, okay, or which is the most efficient path. So, for example, in a GPS navigation system, the podcast might be the total distance traveled from source A to source B. Okay. So it can comprise of what is the fuel cost, what is the travel time, etc. So putting it all together, a such algorithm, okay, takes these five elements as input and produces a solution. Okay. A path from initial state to the goal state, that is considered as the output. Okay. Next, we will talk about problems in AI. Okay. So, what is a problem? A problem is nothing but a particular task or a challenge that requires decision making or solution finding. So, in AI, if you take every problem, must have three things. Okay. First one is the goal state. Second, a set of initial states. Third one is the potential actions or moves. So, what is a goal state? A desired outcome that we are trying to reach or that must be attained. Okay. Secondly, a set of defined initial states. So, what are the possible starting conditions for an agent? Third one, potential actions or moves, the things that the agent can actually do. So, this might sound very simple, but the power of this formation is very, very challenging. Okay, because if you take, for example, a problem of chess, it has multiple states. Like there is a big or there is a very large state space. If you take a medical diagnosis system, that also is a very large diagnostic states. So all these seems to be simple, but all those are very, very challenging. Next, we will talk about problem as a state space. So the formal definition is the state space is a set of all possible states that the agent can be in, starting from the initial state and include all the states that are reachable through valid sequences of actions. Okay, it uses something called as a successor function. Okay, so imagine, suppose you're navigating a city, for example. So your current location is your starting state. The roads you can take as your actions. Every city you could possibly be on the form that forms your state space. And your destination is your goal state. So all this together is called as a state space for a particular problem. Okay. The agent's job is to search through the state space to find a path to the goal. That path to be should be efficient because there must be a multiple parts available. Okay. Next, we will take an example, a chess scenario. Okay. So for this particular problem, how to define the problem as a state space. So as we said, we are going to define the state space for this chess problem. Why? Because it's very complex enough and it's very, very interesting. Okay, right. So to define chess as a state space problem, we need three things. Okay, first one is the starting position. What is the starting position on the board? So every piece in its standard opening position. That's the initial state. Every piece in the sense every coin is in its original position. That's the board with no moves being. All the coins are positioned in its space allotted for it. the rules that define the legal moves. That is the second thing. So each coin in the board has its own rules, own movement rules. For example, a pawn can move forward, okay, and it can take the straight line moves. Likewise, third one, the board positions that represents a win, that is a checkmate. That's the goal test. So every time we make a move, we'll check for the goal test. Okay. Next, we will do the analysis of this. Here, this is a chessboard. Like this is the initial. Like you can see, this is the initial state. Like the coins are positioned, and this is the initial board. And you can see there is a state space being built here. After moving the coins, there is a solution state space being created here. Okay. Each state is represented as an 8 cross 8 board. This is an 8 cross 8 board. An array where each position holds a symbol. Okay. It might be an empty square, or every symbol has its own position. So the initial position was here and it has now moved to here. Okay. The goal state in any board configuration in which the opponent does not have a legal move, that is called as a goal test. Okay. Now, what is a legal move? Okay. So here I have made the space expansion, state space expansion. You can see here. Okay. So it's been moved. I'm showing you this one of the position. Okay. Right. What is a legal move? A legal move, okay, is represented as a production rule. Okay, now we'll just move here for you to understand. Okay, representing the chess scenario. So it's an 8 cross 8 chess board. Each position has its own symbol. Goal is any board position where you don't have, the opponent does not have any legal move. That's a checkmate. What's a legal move? A legal move is represented as a production rule. Okay, leads from the initial state to the goal state. Okay, the left hand side is a pattern matched against the current board. Okay, right hand side, changes to be made to the board position, that is reflecting to the move made. Okay, so this representation is very difficult. Why? Because likewise you have what to say, approximately 10 to the power of 120 board configuration. So it's very difficult. So no person could easily solve it or define the complete set of rules. And no program could easily handle all these rules. Okay. So if you talk about all these things, chess can be seen a problem of moving from initial state through legal moves and trying to reach the goal state, that is a checkmate. So every state has a configuration on the chessboard. So we say the state space is a collection of all these board configurations. So that is what we have to try to understand here. Okay. So though with this more complexity, we can still formally define chess as a state space problem. That is what we have to understand here. Okay, the framework works. Okay. Next, we will discuss about the water jug problem. Okay. So here in this water jug problem, the problem statement is you have two jugs. One can hold 4 gallons of water and other can hold the 3 gallons of water. So if you see, there are no markings in the jugs. You'll just have a jug without any marking. So you cannot measure exactly the 4 gallon of water or 3 gallon of water. So to fill the jug, you can use the pumps just to fill the jugs with the water. So what is the goal here? We have to measure exactly 2 gallons of water in the 4-gallon jug. That is the exact thing. You have to bring it as a goal. The main point you have to understand here is there is no markings in your jug. You have just a jug with nothing, no markings, no measurements. That's a great challenge available. Okay. So how to achieve this? So here the understanding for us is the state space representation. Okay. Here, now we have to formally define everything. Okay. Here, each state is represented as a pair that is x comma y. So here we say x is the amount of water in the 4-gallon jug. So what is the possibility here? It can range from 0 to 4. And what is y? Y is the amount of water to be filled in the 3-gallon jug ranging from 0 to 3. So what is the start state or the initial state? It is a 0 comma 0. Means both jugs are empty. You don't have any water in it. You have to start filling it. So what is the goal? Goal is status you have to have 2 comma n. Okay. Our goal is only we should have the 4-gallon jug filled exactly with 2 gallons of water. That is what we saw. We don't care about the 3 gallons of jug. So the valid actions, okay, valid actions. The assumptions to solve this problem is you can use a pump to fill the jugs. You can pour out the water from one jug to the ground or from one jug to another jug. You don't have any measuring device to do all these things. So you know the operators are very clear here what we have to do. Okay. So the only point is how to achieve this goal. Okay. So I'll come back to this. Before that, this is one of the solution for this water jug problem. What are the possible one of the solution? Okay, so first we can see here, I will just go through one by one. It is the initial condition where both the jugs are empty. 4-gallon jug and the 3-gallon jug is empty. Okay. Secondly, what you try to do, pour all, it's 0 comma 3 means fill the 3-gallon jug. This is 4-gallon jug and this is 3-gallon jug. Fill the 3-gallon jug. Okay. Next, you try to pour this 3 gallon of water into the 3 gallons of water into this 4 gallons. So this becomes 0 and this becomes 3. Okay. Now what you try to do, again you try to fill this 3 gallon. Now both has water, both the jugs have water. Now what you try to do here is, okay, here try and pour the water from 3 gallon here, this is into this 4 gallons. So now this what will happen, you will try and pour the water from here to here. Now this will become 4 and this will become 2. Okay, that's what we are for, we are at 4 comma 2. Okay, now our goal is to make the, this is 4 gallon and this is 3 gallon. Okay, so our goal is this, right? So now what I can try to do is, we are trying to empty this 4 gallons of water. So this jug is empty. Now we have exactly 2 gallons, so we are trying to pour this 2 gallons into the 4 gallons. That is what we are trying to find. So we have reached our goal state. The 4 gallon jug now exactly holds 2 gallons of water. So this step by step sequence is a path through the state space, and finding it is exactly what a search algorithm does. Now here you can see rule 2, rule 9, rule 2, rule 7. So that I will talk now. You can see here we have a set of operators that can be performed. These are the rules, like fill the 4 gallons of jug. So x comma y is the initial state. We can, if I'm having this resulting state, if I fill the 4 gallons jug, I will have the resulting state as 4 comma y. If I fill the 3 gallon jug, then it will have the resulting state as x comma 3. Okay. So if I pour some water out of 4 gallon jug, if there is some water in x, then this is my representation. If I pour some water out of 3 gallon jug, and if there is some water in 3 gallon jug, then this is my state. If I empty the 4 gallon jug, then this is my state. If I empty the 3 gallon jug, this is my state. So pouring water from 3 gallon and 4 gallon, I mean vice versa, this is the state. So pour all water from 3 gallon to 4 gallon, this is the state. Pour all warm water from 4 gallon to 3 gallon, this is the state. So pour 2 gallons from 3 gallons jug into the 4 gallon jug, this is the state, and this is emptying the 2 gallons into the 4 gallon jug. Okay, so these are the rules that can be used to achieve this solution. Like this, you can try and frame multiple solution. Okay, so now this is the state space. I'll just show you the state space, see how it goes, see the water filling, and finally we have reached, okay, 0 comma 2. Now we will do a, common framework. That's a state space representation here. Okay, we are going to do a comparison with the two examples. We have taken two examples. One is the chess, another one is the water jug problem. Okay, in chess, the board positions are the states. In water jug problem, states are represented as x comma y. Okay, that is the pairs. What are the actions here? In chess, legal moves are the action. In water jug problem, filling the jugs, emptying the jugs, pouring the water from outside and into the one jug and another jug, that is the legal moves in water jug problem. So what is the goal state? Here is a checkmate. Here the goal state is 2 comma n, that is exactly the 4 gallons of jug should have 2 gallons of water. Okay, and the final thing is, in both cases, solving a problem means you have to search, you have to make moves. Okay, water operations you have to make in water jug, and moves you have to make a sequential actions in chessboard to achieve a checkmate. So this is the power of state space framework. It gives us a single unified language to describe different problems. Okay, so this is what makes it such a foundational tool in, yeah. So it's very interesting, right? Next, finally, this is the complete framework state. So for the any kind of problem, it might be a chess or a water jug problem. So what all we have to consider? We have to see the state, we have to see the initial state, we have to talk about the actions or the operators, the goal state, state space, and finally the transition model. So with respect to chess, we have the board configuration as the state, and then the initial state as a starting position where the coins are arranged in its particular position. Finally, the actions or the operators are the legal moves, and the goal test is the every move you make, you check whether it is a checkmate. And finally, for the state space, all legal board positions. Transition model is the rules that you have. Each coin has its own moves. So with respect to water jug problem, you specify the states as x comma y. Initial state is both the jugs are empty, 0 comma 0. Then you can fill the jug, empty the jug, pour the water between the jugs. And goal is to bring exactly 2 gallons of water in the 4 gallons of jug. Okay. So the state space is all valid water moves that you can make. The transition model is represented as the production rules as far as the water jug problem is considered. So these are the references I made. Thank you.